Welcome everyone. In this video, we're going to look at an overview of the SCION secure internet architecture. In this first video, we introduce the basic technical aspects of our network architecture. In later videos, we're going to look at the details, but for now, let's get some intuition of how the system works. SCION stands for Scalability, Control, and Isolation on Next-Generation Networks. And we've started in 2009 with the design of this protocol and this architecture. The current project team is composed of Daniele Asoni, Chen Chen, Laurent Xua, Sergio Costea, Sam Hitz, Tobias Klausmann, Yi Teho, Chris Papas, Adrian Perrig, Benjamin Rothenberger, Stephen Shirley, Jean-Pierre Smith, Paweł Szałkowski, Brian Trammell, and Urshan Ukan. And on the picture on the right, you can see us at our annual outage, together with some collaborators from industry and academia. I'll start out by mentioning some terminology. An autonomous system, or AS for short, is a network under a single administrative control. And examples of this would be an internet service provider, or ISP, a university network, or a corporate network. Some large ISPs or some large corporations can also have multiple autonomous systems. Also, we're going to make use of the two terms control plane and data plane. The control plane represents the network functions to explore and disseminate network reachability information. So in essence, it is about finding paths in the network and disseminating these network paths to entities who desire to send traffic. Then the data plane is composed of the network functions to forward a packet. The data plane essentially is responsible for sending a packet from point A to point B. In this slide, we're looking at the main architectural design goals of SCION. First and foremost, we strive to achieve high availability, to guarantee communication between a sender and the receiver. We want to achieve availability even in the presence of an adversary who may control an AS or network routers. In this setting, our goal is to provide availability as long as an attacker-free path exists, such that we can find and use the path for communication. Second, we strive to achieve secure entity authentication that scales to a global heterogeneous environment where not all entities trust each other. We're going to explore this point more in the video on the SCION public key infrastructure. We'd also like to have flexible trust, where an entity can operate in this heterogeneous trust environment and select which roots of trust it wants to rely upon. Also, we'd like to have transparency for a variety of operations. For instance, that it's very clear what is happening to our packets and which entities need to be relied upon for the operation of packets or for the authentication operations. We'd also like to have balanced control among ISPs, senders, and receivers, such that not only ISPs can control networking paths, but also senders and receivers have some amount of path control. Finally, we strive to achieve scalability, efficiency, and flexibility. Scalability, such that we have lower protocol and administrative overhead in large networks and lower than in today's internet. Even though SCION is a security architecture, we seek more efficient packet forwarding than in today's internet. And finally, SCION should have better flexibility to accommodate modern network needs than today's internet. In this video, we're first going to look at the control plane in more detail. How can we find and disseminate paths throughout the network? And specifically, we're going to look at path exploration and path registration. You can also read more about the control plane in chapter 2.1 of our SCION book, which we show how to obtain at the end of this video. Then, in the second part of this talk, we're going to look at the data plane, how to send packets and how the network can forward packets. This also is explained in more detail in chapter 2.2 of our book. And specifically in this talk, we're going to look at path lookup and path combination. One of the most important concepts in SCION is the concept of an isolation domain, or ISD in short. We're making use of ISDs in SCION to achieve high levels of scalability, both with respect to control plane scalability as well as the scalability of trust. An ISD, or isolation domain, essentially is represented by a grouping of autonomous systems. And in this diagram, you see 5 isolation domains in 5 different colors that group the autonomous systems inside of them. So for instance, each circle here represents an autonomous system. The gray area represents an isolation domain core. In essence, it's a set of autonomous systems, or we also call them core ASs, that manage and organize the isolation domain itself. And here we see an example of a core AS. An AS can also belong to multiple SCION isolation domains. For instance, the AS shown here is both part of the core of the green isolation domain and also a regular AS within the orange isolation domain. You can also see the squares that represent truss root configurations, which we explain in more detail in the SCION PKI infrastructure video. The control plane of SCION is split up hierarchically. So we have an intra-ISD control plane that manages communication across isolation domains, and an intra-ISD control plane that manages communication inside an isolation domain. So let's first take a look at path exploration inside an isolation domain. We also refer to this as beaconing. So in this blue isolation domain, we have 3 core ASs, K, L, and M. And these core ASs initiate what we call path segment construction beacons, or PCBs for short. Or sometimes we simply also call them beacons. So these PCBs traverse the isolation domain as a flood to reach downstream autonomous systems. So an autonomous system that receives one of these PCBs can make use of this PCB to extract a path segment that then allows it to communicate with the core AS that initiated this PCB. So next I'm going to show some examples. So here we see 2 PCBs that are being sent by core AS K, and K sends them across the outgoing links that are leading to non-core ASs. So it sends 1 PCB to ASN and 1 PCB to ASO. When N and O receive these beacons, they then update the beacons, as we're going to see in the following video on the SCION control plane, and then they send down these PCBs to their respective neighbors, and so on and so forth. So PCBs traverse the whole network, and in essence, they trace different paths that lead back to the core AS that initiated the beacons. So we can see that the beacons that we followed now define the 4 paths shown here. Similarly, ASL also sends out PCBs. In this case, L has 3 links to non-core ASs, so it sends 1 beacon across each link that again traverse the network as we've seen before. These beacons as well trace the paths that are represented by these orange lines here. And similarly, ASM also sends a PCB that will create this red path. On this slide, I'm going to discuss up-path and down-path segments. As we've seen on the previous slide, the intra-ISD beaconing process sends these PCBs to ASs inside the ISD. And these PCBs contain path segments that can be extracted and used as communication paths to communicate with core ASs. And here we distinguish between an up-path segment and a down-path segment. And note, though, that they're exchangeable. So out of a path segment, one can use it in the opposite direction of beaconing, which then would mean we have an up-path segment. And here the path segment is used from a regular non-core AS to reach a core AS. So for instance, this yellow segment, if it's used in the direction from R to K, it would be used as an up-path segment. If a path segment is used in the same direction of beaconing, we refer to it as a downpath segment. So in essence, the example to go from M to S across the red path segment, we will be using this path segment as a downpath segment. On this slide, we look at intra-ISD path exploration. Essentially, how can we find paths amongst different core ASs? On this slide, then, we show one of these path explorations that are being initiated AST in the orange ISD. We see that AST has several interfaces or several links to neighboring core ASs. And it would send what we call a core beacon across each of these links. So similar to the intra-ISD beaconing, a receiving core AS will resend these beacons to, again, its neighboring core ASs, and so on and so forth. The paths shown here would be traced by the beacons we've just seen. These yellow paths are only a subset of paths that will be found during this beaconing process. For instance, there's of course also a path directly from T to U that will be found, but we just show a few end-to-end paths on this slide. So as we can see, in a well-connected network, a lot of different paths will be found through this process. SCION then also makes use of a path server infrastructure. So essentially, each autonomous system operates path servers. These path servers offer a lookup service. Given an ISD number and an AS number, downpath segments and core path segments will be returned by these path servers. Also, when a local path server is being queried for up paths, this local path will respond with several up path segments to different core ASs. So in essence, the core ASs operate a core path server infrastructure, and then each non-core AS runs the local path server. And the local path servers serve up path segments to local clients, but also resolve and help cache responses of remote AS lookups. In the video on the SCION control plane, we're going to talk about this infrastructure in more detail. In this slide, we look at up-path segment registration, and in the following slide, we're going to look at down-path segment registration. So in essence, we're going to consider ASS with a path server shown here in orange. And ASS essentially looks at the different up paths that it has, and it selects which up paths it wants to register at its local path server that then its local clients can use as up path segments. In this example here, it has 4 different paths, and each path it looks at, it considers this as a good path and registers this path at the local path server. The process is similar for down-path segment registration. So in essence, each AS selects path segments that it wants to announce as down-path segments that others can then use to communicate with this AS. And these down-path segments are uploaded to a core path server in a core AS. So in this example, we're going to again look at ASS, and that's at the paths that it has, and which paths it would register at the core path server. So in this example, again, we have 4 paths that are leading to the core. However, one of the orange paths are undesired by ASS, and the AS will delete this path. However, the remaining 3 paths, it will convert into a downpath segment and upload it to the core path server. Now, once these paths are uploaded, any entity on the network can now query the core path servers for paths to ASS and can fetch these downpath segments. All right, so far we've essentially looked at the control plane. Let's take a look at the data plane, how packets can be sent, and in essence, we're going to look at the path lookup and path combination. Let's first take a look at path lookup. So these are the steps that a host performs to obtain path segments. First, the host contacts a RAINS server with a name. And note that RAINS is the SCION domain name infrastructure. Essentially, instead of the DNS system that's used in today's internet, SCION relies on the RAINS system. So a host would send a request to a RAINS server with, for instance, www.scion-architecture.net. And the range server will respond to the host with an isolation domain, an autonomous system number, and the local address. In case of SCION, for the actual packet forwarding, only the isolation domain and the AS number are necessary. The local address is not really necessary to send the packet towards the destination. It is only used once the packet arrived at the destination AS to be locally delivered. So the host, once it has received the ISD number, the AS number, and the local address, it will then contact the local path server to query for path segments. So the host would send to the path server a request with the ISD X and ASY as shown here on the slide. The path server may have to perform an additional lookup at a core path server, but ultimately replies with an up path segment, a core path segment, and down path segments to the host. And the host can now combine these path segments to obtain the end-to-end path. And this end-to-end path is then ultimately added to the packet for forwarding. I'll briefly talk about this path lookup operation in a bit more detail. However, the video on the SCION data plane will have more details on this process. So a client essentially requests path segments that end up at a given isolation domain and autonomous system from the local path server. If these downpath segments that are requested are not locally cached, the local path server will send a request to the core path server and ultimately replies with up path segments, down path segments, and core path segments to connect them. So in this example here, we see a host inside ASR intends to communicate with a host in ASS. And here the path server replied with the up paths that we can see here, 3 yellow up paths and 3 orange up paths, where the yellow up paths end up at ASK and the orange up paths end up at ASL. Also, several down paths are being returned. We can see that one down path going from K to S is returned, 2 orange down paths from S to ASL, and 1 down path from core ASM to core ASS shown in red here. Now, as you can see, not all the up paths are directly connected to all of the down paths. So in addition, the path servers reply with 2 core paths to make these connections. So 1 core path leading from core ASK to core ASM, and 1 down path from core ASK to core ASL. Now, the receiver that receives all these path segments can now combine them in a number of different end-to-end paths, as we're going to see a bit later. But you can see that there are a lot of different options to form possible end-to-end paths. The path lookup for a remote ISD is not much different. In the example in this slide, a host in ASS in the blue ISD intends to communicate with a host in ASE' in the green isolation domain. And the host would again contact its local path server and request downpath segments to the green ISD and for ASE'. And if the local path server does not have these downpath segments and core path segments stored, it will contact the core path server to request this information. If the core path server does not have the information, it will ultimately contact a remote path server to receive core path segments as well as the downpath segments. In this example here, we can see that 2 uppath segments are being returned, shown here in blue. 4 core path segments are being returned, shown in orange, and 4 downpath segments are being returned. Again, you can see that thanks to the multitude of path segments returned, a lot of different end-to-end paths are possible from S to E'. So let's next take a look at some examples of how paths can be combined. In this first example, we look at a very simple example leading from ASR to ASS. And in this example, we have 1 uppath segment, 1 core path segment shown with the dashed line, and 1 downpath segment. And these segments can be readily combined to form these blue end-to-end paths. In the second example, we see an example of what we call a peering shortcut. I have not explained peering links so far. However, similar to today's internet, where some autonomous systems support peering links between each other, we see that there's a peering link between ASO and ASP. And in this beaconing process that we have seen earlier in this video, this peering link can be announced in the PCB being forwarded through the network. We're going to see more details of this in the video on the SCION control plane. However, for this slide, assuming that the source host has these two paths that both support the peering link between O and P, this peering link can be used as a shortcut. And so the orange up path is used only up to ASO, then the peering link is being used, and ultimately the down path is being used from P to S, offering quite a short path from R to S. In this third path combination example, we see a peering shortcut that will lead across isolation domains. And in this example, we have a host inside ASS that desires to communicate with a host in ASX inside the green isolation domain. In this example, the up path S to M, the core path from M to Y, and the down path from Y to X are being offered. S can see that there is a peering link, and it sees this from the up path segment and the down path segment, that there's a peering link leading from ASP to ASX. And so the peering link can be used to enable direct communication from S to P to ASX. What is important in SCION is the transparency aspect, that for the source it's always visible when a packet leaves a given isolation domain and where it enters another isolation domain. So we're obtaining this very short path, and the source host still obtains full information about how this packet traverses the network. A common case of path combination is called AS shortcut. And essentially it's created by a matching autonomous system on both the up path and the down path segment. In this example, we see that the ASO is both on the up path segment from R to K, as well as on the down path segment from L to S. And in this case, this shortcut can be used such that packets do not have to traverse the core ASs in order to get from source to the destination. And so packets will simply traverse from R to O to S. So in summary, we've seen that SCION is a complete redesign of the internet architecture, which resolves a number of fundamental problems. So the border gateway protocol used in today's internet has a number of protocol convergence issues that SCION all evades. SCION also offers the separation of the control and data planes. We've noticed that in the data plane, packets contain end-to-end paths, and so even if the control plane would stop operating, the data plane could still function and packets could still be delivered to the destination. The SCION isolation domains also offer isolation of mutually untrusted control planes. It also offers path control by senders and receivers. And also SCION routers are going to be much simpler than current routers. Essentially, there is no need for inter-domain forwarding tables. Also in SCION, the roots of trust are selectable by each isolation domain. And this helps with the property of trust scalability we've been talking about. So in essence, SCION is an isolation architecture for the control plane, but it's really a transparency architecture for the data plane, such that it's clearly visible which path a packet can take. I hope you have gained an intuitive understanding of how SCION works. In the following videos, we are going to take a closer look at the inner workings of the control and data planes. In a control plane overview video, we will discuss the details of beaconing, PCB message formats, and security. In the data plane overview video, we will see more details on path lookup, path combination, SCION packet header, in-packet encoding of paths, and security. For more information, please visit our website. Chapter 2 of our SCION book discusses the material we've seen in this video in more detail. You can purchase the book from Springer Verlag, or you can download the PDF from our website. Thank you for watching.